My name is Ross. Welcome to part 2 of the Wally coverage tutorial. In this part, we will learn about how to write a new regression test to improve coverage. Just as a reminder, in the last test our last video, we showed how to modify the RTL to simplify the hardware to improve coverage for an unreachable case. In this video, we'll do the opposite, and we will improve coverage by reaching uh, previously untested hardware. Okay, so just as before, we're going to start by sourcing our setup file. Again, mine is slightly different. All right, so now that that's done, we're going to begin by going over to the tests slash coverage directory, and we're going to just make. So I actually just pulled recently, so to make sure I've got up-to-date tests. And then I'm going to go over to the sim directory, and I'm going to run the coverage regression. And while that's running, I'm going to navigate over to the coverage directory, and we will pull up a specific log file. The one I've got in mind occurs in the FPO. Okay, so just as a reminder here, we're in the sim/cub directory, and we're going to look at the RV64GC uncovered FPU report. So when we open up this file, right, again, it's going to list all of the uncovered um, expressions, branches, finite state machines, and it's going to list them by instances. Now, the one I'm interested in here is the fclassify. This one's a fairly simple module. All it does is it does classification of floating point instructions. So it checks to see if they're, um, nans or, excuse me, or uh, valid values. Okay, so what we can see here is that there's some uncovered expressions. So we can see that there's 4 that are not being covered. And if we look down the list here, we see, all right, here on line 50 of fclassify, you can see that we've got 2 inputs that are not covered at all. And it's saying that XS and X subnorm aren't being covered. So let's open up that file. And if we go over to source/fpu, we open up fclassify.sv. Let's make that a little bigger, and we go to line 50. You can see that that's referring to this one here. So for some reason, we're not generating this subnormal flag or even this XS flag. So the question we need to ask ourselves is, why aren't we generating this? Well, the most obvious answer to this is, well, we're probably not executing a classify instruction with a denormal or a subnormal value. So the easiest way to go about doing this is to go to a floating point calculator and come up with a subnormal value for a floating point. So if we come over to Google and we search for IEEE 754 floating point converter, the first hit is this hschmidt.net website. So this is a really nifty website for anyone who's doing floating point work. So you can actually come in here and generate nice floating point values. You can enter in, decimal values. But what I'm really interested in here is generating one of these subnormal or denormal values. So if I come in here and I say, click one of these bits here, for instance, that this will generate a denormal value as long as I don't set one of the exponent bits. So all I have to do then is copy this hexadecimal representation, and that's going to be our denormal representation that I'm going to want to use. All right, so we'll just keep that in mind while we think about solving our problem. Okay, so now that we know the type of value we need to provide to the software, the question is, how are we going to write our test to to get this coverage. Okay, so if we go into the sim directory go into the tests directory /coverage, you'll find there's a whole bunch of files in here. And the interesting ones to us are the .S files. So if we go to fpu.s, there's a whole bunch of stuff in here already. And this is a place where you can write new instructions to build more testing. So let's do this right at the beginning. So what we really want to do is we want to write a test which is going to um, load a denormal uh, value from memory and uh, send it through a floating point classification instruction. Okay, so to do that, the first thing we need to do is get that value we just created into our program. So if we come back to our calculator, right, let's copy this value here and come to the bottom of our file. And now this is where we're going to do some assembly hacking. So we're going to create a new section in our assembly file, a data section. So we type dot section and then dot data. Let's make this a little bigger so it's easier to see. So that declares we're no longer in code section anymore. This is for data. And then we're going to align it to 8-byte boundaries. I'm going to spell align correctly. And then we're just going to give this a label name. So we're just going to call this test data 1 and then colon. And then because we're going to specify this as a hexadecimal integer, hexadecimal value, we're going to declare it as an int, even though it's a floating point value. So this is the hexadecimal integer representation of that floating point number. So, right, this is, a denormal floating point number. Okay, so now what we need to do is we need to load that single precision floating point number into a floating point register. And so we're going to do that by reading that from memory. And so we need to load into a GPR that address, which it comes from, what did I call it? Data, test data 1. So this is going to put that address into T1, and then T1 plus 0 will be the address of that memory, and we'll load that into FT0. And then the last part here is now we need to actually execute a classify instruction with that data. Okay, so now to do that, let's look at the RISC-V assembly manual. So if we come over to the non-standard specification, that's the 2019 December 13th edition, and we can come here and see that the name of this instruction is fclass.s. And if we come down to the assembly listing, we should see that in here somewhere, hopefully. Yeah, right here. So we can see it takes an RD and an RS, and so the RS is going to be the floating point register, and the destination is going to be a GPR, an integer register. So it's going to be fclass.s, and let's just make our destination T1, and the source will be FT0. Okay, so now we need to build this test. So we'll cd into test/coverage, and we'll make it. And it looks like I have a typo somewhere in here. So this is good because now you get to see what an error looks like. And this is not the correct syntax for a load. So it should be FLW. So let's try that again. And I didn't save the file. Okay. Okay, so now it's compiled, so we should be good. If we go back to our sim directory, okay. And now if we run our regression test with coverage again, we should hopefully see that our coverage report doesn't contain this message again. But before we do that, what I want to do is I want to actually open up the coverage report that shows everything, not just the uncovered results. So that's this one right here. And I want to actually make a copy of this so we can compare it to the old one. So this will be coverage fpu old.rpt. Okay, now let's run this regression with coverage. So once this is done on the left-hand side, I will have the old report, and then on the right-hand side, we'll have the new report. And if we did everything correctly, we should see that we are covering those 4 cases that we were missing. Okay, so our coverage report is completed. And if we go to FPU coverage report, make this a little bigger so we can see it. So I'm going to search for F classify in both of these. Okay, let's put these both at the top of the page. Okay, so we'll see here, we see F classify. We got our expressions, we got 20 bins, 16 are covered, so we got 4 misses. And over here on our new version, we've got 20 bins, 20 of them are covered, so there's no misses. And if we go down to the specific lines that were not covered, that was line 50, we see here we got 2 out of 2 are covered, and previously we had 0 out of 2 are covered. So that shows us how we can write an extension to the regression test to add coverage. Now there's something really important to mention here is this didn't prove that we actually demonstrated the hardware worked correctly. All we did was we extended coverage. If we want to show that we want to show that the hardware actually performed correctly, we actually need to write the test in either a way that is self-checking, or we need to have some sort of external mechanism to show that the hardware matched some other reference model. And for that, we can use something like ImparisDB. And that's beyond the scope of this video, but I hope you found this video helpful. And with that, that concludes this tutorial.